Thanks everyone for coming. I'm excited to be here again since I wasn't able to present a couple weeks ago. But yeah, like Luke said, this is a first look at the large ensemble that we've been generating using DOE resources with the E3SMv version 1. Yeah, and Manu is the PI. Our project is focused on understanding the mechanisms of Pacific decadal climate variability. But I'm not going to be focused on that specifically today. This is just like an overview of the ensemble itself. So I don't know, I probably don't have to tell this crowd a huge amount about large ensembles, but just to emphasize that they are kind of gaining popularity within the climate modeling community. The CESM large ensemble is a particularly well-known example, but there are many others at this point of different sizes. They have typical sizes of anything from like 15 to 20 all the way up to 100 members. That's the largest one I know of right now is the NPI Grand Ensemble. And this figure is just adapted from the NCAR Multi-Model Large Ensemble Archive webpage. So we're trying to, there are these ongoing efforts to not only run multiple large ensembles with different models, but also facilitate the intercomparison of large ensembles. And so I think that's pretty exciting for the community, but it's important to run as many large ensembles as possible so that we understand the potential range in internal climate variability and the relationship between internal climate variability and model physics or other aspects of the behavior of the model. All right, so this is the kind of point today is that the E3SM version 1 is a really new model. So that's exciting, right? It's like the DOE model, obviously, and its internal variability is largely unexplored. I believe there were 5 simulations that were submitted as part of CMIP6. Luke can correct me if I'm wrong about that, but it's not really sufficient for many aspects of exploring internal climate variability. So what we wanted to do as part of this PDV project was to try to run additional members to get a sense of the potential range of variation. So this is like the brief statistics on the large ensemble that we've generated so far. We've decided to target 20 ensemble members, which is largely limited by the amount of computational resources that we've been able to get so far. It's been run at low resolution, so that's like for E3SM, that's about a nominal resolution of 1 degree in the atmosphere. I think it's got regional resolution refinement in some places. And I just wanted to acknowledge the resources that we've been given for this ensemble, as they've been hugely helpful. A lot of these simulations were run on Cori as part of a NERSC allocation, and Brenna was nice enough to help us with access to the Compi facility as well. So thanks very much for that. That's been amazing. So far, we've been able to complete these 20 members, but only for the historical period, which is 1850 to 2015, in compliance with the kind of CMIP6 standard time periods. We are working on finalizing the comp set for the SSP370 in order to do the 21st century projection portion of this ensemble, which will go from 2016 to 2100. So that time scale on that is probably very in the near term. I'm hoping to get that squared away in the next few weeks or so. So we should be able to start generating those members at that time. But for right now, we're working with the historical period, which is already pretty cool, I think. So I will be presenting that today. So yay, check mark on the historical runs. All right, so how do we actually do this? There's, as I'll touch on in a minute, there's many different ways to initialize a large ensemble with a climate model. We are using what's beginning to be referred to as a macro initialization strategy, where we took the existing low resolution pre-industrial control and picked different initialization years to branch members off of for the historical period. So this is just a schematic illustration. So the gray line is, I think this is surface air temperature from the PI control. Doesn't super matter. It just kind of illustrates variations, and that we are choosing these different macro states. So the reason why it's valuable to choose these different years within the PI control is that they are atmosphere and ocean states which are in equilibrium with one another, and they kind of sample more of the range of internal variability than you might if you only, say, perturb one component of the model, like the atmosphere, which would be a micro initialization strategy. So yeah, so we picked these different years to branch members off of and restarted them from the PI control. which is yeah. But I guess I did want to mention that the way that we chose which years to branch off of is somewhat novel in the context of other macro ensembles. Because we were fairly computationally limited, we wanted to be as smart as possible about choosing initial states that were as independent as possible. So the way we chose to do that is by figuring out what the state of each ocean basin was as a function of time and try to pick states that were as independent as we could. So this is just an illustration of the method, or one aspect of the method. It's the correlation of the, all right, so let me back up. And we took the first PC of the 8-year low past ocean heat content over the upper 300 meters. I guess it's temperature, but it's kind of proportional to ocean heat content. And made indices of that for each ocean basin. So and we found that the Pacific and the Atlantic tended to diverge the most. So we also did the Indian and Southern Oceans, but the Pacific and the Atlantic had the most kind of independent degrees of freedom, it seemed. I'm not showing that here, but this is just like the correlation patterns of surface temperature, so you can get a sense of the spatial structure of that variability. So in the Pacific, obviously, there's more of a Pacific loading, and in the Atlantic, there's an Atlantic. It's probably more related to like AMOC variability. But these are just kind of the modes that you tend to see in these basins. Right? And so how do we pick time periods where these particular modes are most independent? Well, if you construct a phase diagram of the time series of these first two PCs, so here is the Atlantic is plotted on the x-axis and the Pacific on the y. So you can see it's like a lot of squiggles. It has this like fairly complicated trajectory in phase space. And we went back and forth on several methods for this, but said, okay, well, we have this phase diagram. It's kind of a big blob, and we're going to evenly sample throughout phase space in both dimensions and pick, you know, if you imagine like a grid throughout phase space in both dimensions, then you would want to pick, you know, points that are actually on the phase, the trajectory of the actual system. And you want time years that correspond to restart years in the PI control. So yeah, oh, I thought I had another slide on that, but I don't. So yeah, so basically this was our best attempt at fully sampling the independent variability between the Pacific and the Atlantic. So we think that this is perhaps more a more efficient way to get to independent variability than other ensembles which use macro initialization strategies as well. Although, as I'll get to in a minute, it's unclear exactly how much this makes a difference. But I think it's a good strategy if you're limited in the number of members that you can run. Okay, so what does this actually look like? How are we doing? All right, so we've done some initial validation of the ensemble. So here is just, you know, because we used ocean heat content as our method of initialization, we're trying to see how it compares to observations. So in this case, ocean reanalyses. So we use the GECKO3 and ORAS4 to compare with E3SM. And it looks pretty good, I think. We still need to maybe quantify this a little bit more, but it is comparable to the magnitude of ocean heat content in both reanalysis products. And I'm putting both of them on this slide just to illustrate that within reanalysis products, there's also some degree of disagreement. That's, yeah, there's, the reanalyses don't perfectly agree with each other, right? So this is over 1958 to 2005, that's the reanalysis period. So we think this is a reasonable representation of reality. Another thing that E3SM seems to do well at is representing the teleconnection structure of Pacific variability, climate variability. So here is just the ENSO teleconnection pattern. That's just the regression of surface air temperature in colors and sea level pressure and contours on the Nino 3.4 SST anomaly. Right, so E3SM is on the top, observations on the bottom. And so you get the El Nino-like pattern that you would hope you would when you regress on Nino 3.4. But the magnitude and location of the Aleutian low influence from ENSO is fairly good in E3SM. You know, some models have, you know, very overly weak or strong or like weirdly located teleconnection patterns. So we think this is pretty good overall. And do I have a slide on this? No, I don't. The magnitude of ENSO is also fairly accurate in E3SM. So, you know, So that's always somewhat by accident in these models, but it's at least a positive sign that E3SM is going to be a useful tool for understanding Pacific climate variability and its impacts. Right, so that's kind of the positive aspects of E3SM performance. Where it seems to struggle a little bit more is in things like representing the trajectory of 20th century warming. So this is the time series of global surface air temperature anomaly relative to, I believe, 1880 to 1910 or so. So we've got several different observational products that are shown in the colored lines, and then E3SM is in the gray envelope, and the ensemble mean is the black line. All right, so it's, and this was documented in the CMIP6 submissions as well, but it's a fairly flat temperature trajectory for until about the 1970s, and then we get this perhaps overly rapid surface warming in the later part of the 20th century. And this is most likely a result of the sensitivity of the model to aerosol forcing. What's kind of interesting is that if you look at the temperature time series regionally, it seems like there's a pronounced spatial structure to it, right? So here's just the same thing, but for North America on the top and the North Pacific on the bottom. And you can see that North America matches the observed temperature time series a little bit more closely. It's still somewhat too flat until around the 70s, but it's less pronounced than was the case for the global average. But in the North Pacific, you really see this pop out, right? So there's an extremely flat and, in fact, pronounced cooling from the 50s to about the 80s in the North Pacific. And then it recovers, and we see that kind of strong surface warming begin again. So we're interested in the aerosol forced aspect of Pacific decadal variability, and it looks like if there's a strong loading over the North Pacific, then this could potentially have a systematic impact on modes like PDB. So that's something that we're exploring at the moment. So yeah, I just thought that was kind of an interesting feature. But I guess the other scientific question that we're raising with this ensemble is, what does this tell us about how, what are the advantages of this macro versus micro approach to ensembles, and what does it mean about maybe how we should be building them, or when we should be thinking about one versus the other? So I don't think this is something that's been thought about in too much detail yet, because it's still pretty new to have enough ensembles to even do this kind of study. So I'm pretty excited about it. And so what we're trying to do here is compare E3SM to other CMIP6 era large ensembles, with the exception of CESM1, which is a CMIP 5-ish era model, but we had to include that because it's actually the only micro ensemble that was available. So here's E3SM. E3SM is the ensemble that we ran, and then the other 5 are existing large ensembles with other models, right? They all start in 1850 with the exception of CESM1, and they have ensemble sizes of 20 to 50 members. Okay, so those are the ones that we've been able to work with so far. And what we wanted to do is ask the question, okay, if you're initializing your model differently, what does that mean for the initial ensemble spread? And what does that mean for the evolution of ensemble spread throughout the course of the simulation? So the metric that we're using for this at the moment is the standard deviation of ocean heat content across ensemble members. Right, so if you imagine you plotted the ocean heat content for every ensemble, you would have some time series, and then you just take the standard deviation across that, and you can do that as a function of time. So this is just what you get if you do that for month 1 of each simulation, which again is January 1850, I think January probably, for all the models except CESM1, which is 1920. Okay, so obvious features are, the micro ensemble has the smallest initial spread, right? Makes sense. That wasn't the case, we'd worry that we did something horribly wrong. But there's potentially interesting differences in the spatial structure of this initial spread that, again, we're still kind of working on understanding. E3SM seems like it may be regionally larger than some of the macro ensembles, particularly in the tropical Pacific, which was our hypothesis, right? It's because we've tried to optimally choose the initial states of the Pacific and the Atlantic to be maybe more independent than other ensembles. We were hoping to see a systematically larger spread. We don't see that everywhere, but perhaps somewhere or in some places. But it seems like some other macro ensembles, in particular EC-Earth-3 and CNRM-CM6, have larger spread in the North Atlantic. So not sure exactly what to make of that, but it seems like, again, there's not an obvious systematic difference between the macro ensembles, at least not one that we've been able to dynamically explain so far. So then I mentioned this idea of building a time series of ocean heat content. So here's actually the time series of the standard deviation of ocean heat content across ensemble members as a function of time. Right, so the region that we're using here is 60 north to 60 south. So we're trying to exclude explicit sea ice coupled influences, which might be a thing we want to think about next. I don't know, but you can see that this standard deviation is different on average between the ensembles. So in particular, CESM seems to have a much smaller standard deviation than the other simulations, which, I don't know, it could just be a feature of CESM's internal climate variability. The next thing that we're going to try to do is to normalize these by the variability within the PI controls of each simulation. We just haven't gotten to that yet. But yeah, and E3SM seems to be has a higher standard deviation of ocean heat content. But what we don't really see is the other macro ensembles starting out at a lower standard deviation and then having that rise quickly in the first year or 10 years of the run and then equilibrate to a different level, which is what you might expect if there's some systematic influence from the different macro states. There's some hints of that potentially in CNRM or, yeah, I think that's the only one, maybe, but I wouldn't put a huge amount of stock in that yet until we've done some other analyses. But yeah, I guess, I don't know, we're still like exploring this a little bit, so I would be happy to get feedback from the audience on this. And I think that might be no. Oh yeah, then the other thing is there may be more to this if you look at regional differences, right? So I mentioned that E3SM seems like it has a larger initial spread in the Eastern Pacific. And we do see some of the other models starting out at a lower standard deviation in the Eastern Pacific and then rising to a different level. But again, there's a huge amount of noise. So we still need to confirm that this is, statistically significant and all that. But, in particular, like EC-Earth has a lower spread. CESM, obviously, it's actually at 0. I don't know how easy that is to see in the black line on this graph. But CNRM also has a lower spread initially. So I think this is at least a useful way to think about how initial states influence ensemble spread. But again, there's a lot of still scientific questions left to be explored. Okay, so those were all the results that I had for today. Just to reiterate, the E3SM version 1 large ensemble now exists, and it's going to be a new resource, and it will have future simulations probably, I don't know, in the next 6 months, I hope, depending on the kind of computational and human resources we can apply. E3SM is good at many things. In particular, it represents the mean ocean heat content pretty well, and it's pretty good at things like ENSO teleconnections. It tends to underestimate the global mean and the North Pacific 20th century temperature trend until later in the 20th century, which may have implications for aerosol forcing of climate variability. This initialization method that we tried, like optimally spreading out initial conditions across basins, seems like it has some possible indication of actually being more optimal than others. Maybe, but the signal seems to be somewhat small. So I think the kind of big picture takeaway from this is that you definitely want to be doing macro initialization, right? So that like all the macro ensembles had higher initial spread than the micro ensemble, but it's still somewhat up for debate about how the particular macro strategy matters. And it might be that all macro methods are more or less created equal, but it might matter more if you're interested in like smaller scale features of climate. So yeah, so that's all I had. Thanks again for listening.